Thank you for coming to our session on the 2020 Simeonov Island earthquake. Today, I will be talking about how the Simeonov Island earthquake relates specifically to the October magnitude 7.6 sandpoint earthquake, which is further to the west of the Simeonov earthquake. I'll start out by addressing what questions we're interested in answering with respect to the sandpoint earthquake. The map on the right shows all of the aftershocks recorded by the Alaska Earthquake Center following the July Simeonov magnitude 7.8 earthquake. The aftershock activity from July to October was primarily westward and down dip of the main rupture, effectively closing the Shumagon Gap from 30 to 60 kilometers depth. The October Sandpoint event and its aftershocks are up dip and roughly orthogonal to the aftershock distribution. This is a peculiar pattern and leads us into our primary questions. First, how are the Simeonov Island and Sandpoint earthquakes related? Secondly, where was the slip concentrated for the Sandpoint earthquake? Was there slip along the subduction interface? Third, how do we explain the observed tsunami? Why was the tsunami larger than the Simeonov tsunami? And finally, is the Shumagon Gap now closed, or is there still potential shallow slip that can be accommodated? I wanted to start out by describing what is the Shumagon Gap. The figure here shows the major ruptures along the Alaskan subduction zone in recent history. The Shumagon Gap is a region that has not had significant earthquake ruptures since about 1917, and thus poses a potential hazard for generating large megathrust earthquakes. Both the Simeonov Island and Sandpoint earthquakes were within this region. For understanding the seismic hazards in the Shumagon Gap, it is important to have a handle on the plate coupling in the region. This is a figure from Lee and Freimuller that shows the locking fraction. That is 1 minus the ratio of slip on the fault to the plate convergence rate. In the Alaskan subduction zone, the Shumagon Gap is the transition zone from the highly locked Kodiak segment to the east to the freely slipping Sanak segment to the west. Even though the locking of the Shumagon Gap is low, there's still some interseismic strain accumulation that can generate on order of 1 to 2 meters of slip every 100 years along the shallow megathrust. To start out discussing this earthquake sequence, we need to start from the rupture process of the Simeonov Island earthquake. The plot on the left shows the coseismic slip model. The plot on the right shows the following 2 weeks of coseismic slip. The main shock ruptured down dip and towards the west, closing part of the Shumagon Gap between 30 and 40 kilometers depth underneath the Shumagon Islands. We showed in our paper that this rupture was reminiscent of the 1917 rupture in the same area. The post-seismic slip is not as well constrained, but it does show that most after slip was down dip of the main shock, and there is probably little shallow participation on the megathrust towards the Sandpoint earthquake rupture. This figure shows the NEIC finite fault model for the Sandpoint earthquake. The fault plane is based on the W phase solution of 350 degrees strike, 49 degrees dip, and right lateral slip. It is important to point out that the double couple percent for the W phase is almost 71%, so there is a high likelihood of additional faulting here. The fault plane also includes intra-slab slip and slip in the overriding plate, where much of that southern slip patch is beneath the top of the slab. However, this earthquake generated a fairly sizable tsunami for a strike slip earthquake, with peak amplitudes between 0.5 and 1 meter at the closest tide gauges seen on this plot. We performed a simple forward model to determine the seafloor deformation required to match this observed tsunami of the tide gauges and dark buoys nearby. Up dip of the Sandpoint earthquake, there needs to be 0.5 to 1 meters of uplift on the seafloor. But when you look at the seafloor deformation generated by the NEIC model, the uplift is much smaller and not distributed enough spatially to generate the observed tsunami. This is the first inclination that an additional fault is needed to appropriately model the Sandpoint earthquake. Even more peculiar is when you overlay the slip model of the Simeonov Island earthquake on the seafloor deformation required to generate the Sandpoint tsunami. When you do this, you see that the patterns fit together almost like a puzzle. I'll show this as I fade this figure in and out. So to model the Sandpoint earthquake, we used MudPy, which is a kinematic slip inversion package. We include 5 1 Hz GNSS stations and 4 strong motion stations, which we downsample to 5 Hz and integrate into velocity after gain correcting these stations. The GNSS data we process using ChIP-SIG-X and final orbits. The Green's functions here are obtained using a frequency wave number approach, and we include 8 triangular source time functions to allow for variations in rupture speed. In the inversions, we search for the optimal rupture speed and the smoothness constraints. For the faults, we test 3 different scenarios here. First, a strike slip only geometry based on the NEIC solution. Secondly, a slab only solution that uses the same fault discretization we use in the Semyonov earthquake. And a third scenario that includes both of these geometries. First, the strike slip model does a fairly good job of modeling most of the data, and we obtain a model that is very similar to the NEIC model, even though they did not use GNSS data in their solution. The fault patch towards the south is mostly intraslab. We do find that the seismic data to the east is very poorly fit in this case, and the vertical signal at AC12, the closest site, is underfit, which this is problematic for generating the appropriate tsunami here. The slab-only model is interesting in that it does prefer slip up-dip of the Semyonov Island rupture. However, we're fairly confident that this earthquake was not only on the slab due to the very poor data fits that we see here. When you invert for slip on the 2 planes together, though, the resulting slip models look similar to the single fault models. However, the magnitude of slip is somewhat muted here. It is also interesting that all of the slip on the strike slip fault appears to be intraslab in this inversion, even though no constraints are placed on the slip. The slip on the slab does not extend too far up dip, indicating that very shallow strain was not released, although the coupling models would indicate that not much strain is being accumulated here anyway. Most importantly here, the data fits are much better than either of the single plane solutions, indicating that participation of the shallow megathrust was probable. Those 2 stations to the east, the seismic stations, they're much better fit in this case, and then the verticals at AC12 are almost perfectly fit. I think the question everyone is interested in is, have we closed the Shumigan gap after this event? Looking at the 2 ruptures and the aftershocks from the Semyonov earthquake, it is not likely that the western up-dip part of the Shumigan gap is closed, and there's still potential for more strain release in this region. I also think better understanding the 1946 earthquake, which had a very slow rupture speed and caused an abnormally large tsunami, will be the key to understanding the future tsunami-genic potential in this area. Moreover, additional activation of splay faults in this area is an ongoing concern for tsunami genesis. So in conclusion, the Sandpoint earthquake ruptured both an intraslab strike slip fault and the shallow megathrust. The megathrust participation was probably not large enough to reduce the likelihood of another shallow rupture in the Shumigan gap. We just simply don't see enough slip on the megathrust to indicate that that's the case. We still need to take our slip models and forward model out the tsunamis to determine if our dual fault model is the correct model. And we also need to do additional testing here to determine what the appropriate strike slip geometry is. In this case, we use the NEIC geometry, but do we want it to be more vertical than that solution? So thank you.